Hey folks, this afternoon's MA 125 section here. I want to look at some of this trigonometry that we're working on now. I want to do some examples from there and I'd like to answer some questions if you're on with me. Drop some stuff into the comments here. Not much more to say, so I'm going to get into some examples here. Hope you can join us as we go along with this. Trigonometry basics that we're trying to cover, how to work with the relationships between the sides and the angles in a right triangle, and how that stuff fits into the XY plane or the unit circle, to build on that idea to be able to handle angles that are out in the other quadrants. Let's work some exercises on it and I'll get this set up. So I had a preview for this stream. I had the little thumbnail from this stream that showed the picture of our college algebra hill. But the book that we're in for the trigonometry is, of course, our second book on this, which I don't have a physical copy of it at home. I left mine in the office, but it's all available here on the XYZ textbook site. So I'm going to work some exercises out of there. I hope you've gotten into the textbook site on this. I noticed working on it in XYZ textbooks. This is a one chapter book, so you have access to the whole thing up here. And I was just looking at some of the exercises from here, and the examples off to the side have the nice video explanations on them. So I think there's an awful lot of what you need that's right there, that as you're working on these exercises, you can work these caption video. You can run these caption videos that are right there on the side that have similar questions. So you can see the process pretty well from that, but I want to work through some of them myself while I'm on with you, and certainly help anybody that's gotten stuck on any of this. So I'm looking at what is page 22 of this trigonometry book. Which is section T2, and here are the exercises on that. I'm going to work on number 14. Which shows the actual triangle here. It's drawn in the book, and I'm going to duplicate it here so we have it in front of us. Theta is our angle down in here. That's the typical variable used for an angle. And we have 6 down here, and we have 3 square root of 5. And it looks like we're finding theta, but what they're actually asking for here is the exact values of the 6 trigonometric functions of theta. So we're not actually finding the angle, we're finding the values of the functions, the output values of these functions, which are just ratio things, not actually finding the angle itself. Finding ratios of it. So all of these functions that are introduced in here, I'll list them because we have to answer all of these things anyway. So I want to know what sine of theta is, and what cosine of theta is, and what tangent of theta is. So these are introduced in here. And then the other 3 kind of go with it. I'm going to write them next to this because they kind of go together with what's happening. The cosecant of theta is one of the fancier ones, but it's just the reciprocal of sine. And secant theta is the reciprocal of cosine, and cotangent theta is the reciprocal of tangent. All of these are defined as ratios or a fraction. So the reciprocal of a fraction is very easy to do, and they have their own name right there. We're not going to see these names very often. We don't work with them very much, but we should know what they are. And this problem says to find all 6. So we're going to work with all 6 of those. Label some stuff that I got here. That's the angle that I'm dealing with in a right triangle. So I should have a little mark right here showing that this is the right angle in the thing. Across from the right angle, you have the diagonal side or the longest side, and this is called the hypotenuse. That's the fancy name for this. That's not going to work at an angle. This is your hypotenuse. These two sides are called the legs down here, but to distinguish them, one of them is across from the angle that we're talking about, and one of them is right next to the angle that we're talking about. So this one is called the adjacent side, and the other one is called the opposite side. And notice we don't know the length of this. It's not given in the drawing here. We have to work that. We're going to figure that out first, and then we're going to fill in the answers to these 6 trig functions down here. But it's a right triangle, so Pythagorean's theorem applies to this. I'm going to do some work off to the side to figure out what this opposite side is. But I know that if you call them A, B, and C, this is true, where C is the hypotenuse. So 3 square root of 5 squared is supposed to equal the sum of the squares of these two things. 6 squared and my unknown opposite side over here. So that's the one I'm trying to find. I'm going to work through that. Let me square the things that I know right here. 6 squared is 36. 3 square root of 5. If I multiply that by itself, I get 3 squared, which is 9, times the square root of 5 squared, which is 5. So I got really 45 right there. The opposite squared. 36 plus the opposite squared is 45. So the opposite squared has to be 9. So the opposite side there is just 3. Square root of 9 is just 3. So that's what I've got right here. That's going to be the third side for the triangle. So I got all 3 of those values. You can make ratios of them in different ways. And that's how these functions are defined. I like to put containers here for functions. They're not always written like this, but there's an advantage to writing them so you keep track of the input into the function. This is not a thing. Times theta, this is a function, and this is the input into the function. The input's always the angle, which we don't know. The output for these functions is a ratio of stuff. And sine theta is defined to be the opposite over the hypotenuse. So that's 3 over 3 square root of 5. And these are similar. Cosine is the adjacent over the hypotenuse. And tangent is opposite over adjacent. So 3 over 6. And these 3 are defined similarly, except they're the reciprocals of these. This is hypotenuse over opposite. This would be 3 square root of 5 over 3. I'm going to go ahead and do the reciprocals now because it's really easy to do reciprocals of fractions. This is 6 over 3. Of course, all of these things could be written in a little bit simpler form. I'm writing kind of small on this. I should probably try to write a little larger. But this simplifies to just 1 over square root of 5. And this one to 2 over square root of 5 because you can divide them both by 3. This is just 1/2. This is just square root of 5. This is just square root of 5 over 2. And 6 divided by 3 is just 2. That one's larger. So you can see the reciprocal relationship going on there. Now, this way of writing things isn't great because we have radicals in the denominator. So really the proper form when you have a number like that is to write it without the radicals in the denominator. So I'm going to rationalize. We went through how to rationalize these things, and we're not doing anything fancy here, but I'm multiplying top and bottom by square root of 5 to make that denominator come out nice. That's the skill we used earlier, and that's one place we use it a lot, is in these ratios. You get denominators a lot. And because these numbers work in Pythagorean's theorem, we end up with square roots an awful lot. So we'll see that kind of those kind of values showing up in a bunch of these problems. I want to make a connection here to try to lead into where we're going next and where else we're going to be working on this stuff, just to while we've got a nice problem ahead in front of us, let me look at something a little different on this one and lead into the next section where it talks about trig functions of any angle. So that triangle that we had right there could live in the XY plane. But I want to think about that triangle. What would happen if we wrote it this way? It's really the same triangle, but I'm going to write it upside down. So that adjacent side was 6. This hypotenuse over here is 3 square root of 5. And this opposite side is 3. This is really the same triangle, but if it's drawn this way around, there really is something different going on. Still a right angle in it. There is a little bit different going on. The direction that this is facing is a little different. We'd like to keep track of that. When we're doing angles, we measure from the horizontal up. So theta would be this nice angle here that looks like, I don't know, 20, 30 degrees somewhere. I don't know what the angle itself is. This is kind of going the opposite direction from the horizontal down, or almost all the way around. If we thought about this thing living in the XY plane here, we actually measure angles according to this scheme that starts at 0 degrees here, goes around to 180 degrees, keep going around. We're going to be almost to 360 when we get here. So this is 300 something. This angle is really in a different quadrant. And instead of just thinking about the sides of these things and how long they are, we can actually think about this as positive or negative values to determine which direction this is going. The 6 is going to the right as a positive 6, but the 3 going down now, when I flip this thing over, I could really think of this as a negative 3. The length of it is still 3 units in the triangle, but since it's going in the negative y direction, I could call that side a negative 3 instead, and that would work nicely. With the coordinates of this point down here, if this is the origin, this is positive 6 and negative 3 are the x and y values of this thing. And it's the same triangle, but it's including that negative sign in there kind of tells me how it's positioned, and that gives me a little bit more information about it. And that y value being negative would actually change the output of some of these trig functions up here that involved the 3. That would actually come out negative now if we were talking about this one. So that's gonna be how we apply these things in this next section. In the regular right triangle stuff, sine theta is opposite over hypotenuse. They're abbreviated this way. Because I don't know, it's trigonometry, and be like 3-letter abbreviations to things in trigonometry. But opposite over hypotenuse, when you're talking about a regular triangle thing, but when we move it out here into the XY plane, that's really the opposite side is the y value over here. Your theta is up here by the origin, and the y value is taking the place of the opposite side. So this is really y, and this hypotenuse is the distance from the origin to that. It's called r. And so sine is y over r, and likewise cosine, which in triangles was adjacent over hypotenuse. When we go into the XY plane, the hypotenuse is r and the adjacent side is your x value. That's the same as your x coordinate right there. It's how long this triangle is in the x direction. So we get these things instead of opposite, adjacent, and hypotenuse. We're thinking about x, y, and r, and that the x and y are allowed to be negative to show what quadrant we're in. That's how we're going to generalize this, so we can think about triangles that are situated differently or sort of angling into a different quadrant. Right now I want to work some more stuff right out of this section T2, though, before we get into those other quadrant things. I'm going to stay in T2 for now, just working triangles for now, because I want to make sure we cover the basic ideas. So back into these pages. They have some angle of depression, angle of elevation kind of questions in here, so I might as well do something describing what that looks like. Number 75 in this section Talks about angle of elevation. Elevation is how high something is, and the angle of elevation, when you see that word, that means it's an angle measured from the horizontal. You're in a situation where you've got some kind of level or horizontal to look at, and you're measuring an angle up above that. So if this is your angle of elevation, it's just measured from the horizontal. That fits nicely with how we do things in the XY plane, because we measure starting at 0 degrees being the horizontal at the x-axis, and we measure the angles that way. So this angle of elevation makes sense for them. In number 75, we're talking about the angle of elevation of the top of a hill from a certain point on the surrounding level ground. So our horizontal would be this level ground, and then we've got a hill in it somewhere. And the angle of elevation of the top of the hill is 10 degrees. So we're looking at it from somewhere over here on level ground, and we've got a 10-degree angle there. It says the hill is 9 feet high. What is the horizontal distance to the top of the hill from that point? So we know the height measurement is 9 feet. We want to know how far we are away if this is a 10-degree angle. So there is a right triangle in the picture from the top of the hill. Straight up is 9 feet. So that's 90-degree angle with the horizontal. And we do have this right triangle formed, and we can use some trigonometry stuff. We want to know what is this adjacent side down here. I'm just going to call this x. This is my unknown side, and the 10 degrees is over there. So this is where we're going to need calculations involved. We know the angle. We're going to have to work something with that. But the relationship between these things is one of those things that I already wrote down. This is your opposite side, or y, and this is your adjacent side, or x. So I can look at the ratio of these things, and opposite over adjacent was the ratio that we called tangent. Opposite over adjacent, or y over x, is what we called the tangent of the angle. So tangent of 10 degrees is supposed to be y over x. So for this problem, we have y is 9 feet, and x is the actual unknown. So the tangent of 10 degrees is supposed to equal 9 over x. I can solve for x and that with a little bit of algebra, but I just want to know what the number is. What is the tangent of 10 degrees? That's not one of the nice things that we memorize values for right there. 10 degrees is not one of them. So we're just getting the approximate value from the calculator. I need to make sure this calculator is set to work in degree mode then instead of radian mode. So I'm going to have to think about that. Angles. I'm going to change this to degrees. Okay, so I'm dealing with degrees now. Different calculators, it's different. I had a setup menu in this one.
Oh, I got second place.
Where that is in the setup menu, but different models of calculator. There's a way to change from degrees to radians to maybe some other stuff. But we want that set to degrees for what we're working on now. And then out of that. I'm just looking for what is the tangent of 10 degrees. That's the calculation that I'm doing. So tangent of 10 degrees. 0.1763. So if you do tangent of 10 and you get a different number, it means you're probably not in the right mode. And we need to work on or look up your instructions on how to deal with that calculator to change modes. We're going to see both degrees and radians, and we're going to change back and forth on that. One of the things to get used to in trade. It's a little bit like feet and meters. I mean, they're both perfectly good systems, and both of them are commonly used. So you need to know how to deal with either of those systems and convert back and forth. But the tangent of 10 degrees is 0.1763. Now that's approximate, but I'm going to round it there and go with that. 0.1763 is supposed to equal 9 divided by x. So x times 0.1763 is equal to 9. I'm just doing the algebra out on it now. I got to divide by that decimal. I got to do 9 divided by 0.1763. See what I get for that. So another calculation, regular division. Divide by something that small, I'm going to get a much bigger number. That comes out approximately 51. And so I know that the x value is about 51 feet up here. Units, if you're doing ratios, the units are the same. So since that was 9 feet, the x is 51 feet. That's going to be your distance from the hill, which is what they're asking for in that problem. A lot of things in life that are not easy to measure directly are easy to calculate using trigonometric relationships between them. If you want to know how tall a skyscraper is, they don't really let you climb up there with a tape measure, right? It would be really hard to run a string from the top to the bottom or something. Hard to directly measure, but if you can stand back and figure out your angle of elevation, and you can measure the horizontal distance along the road nicely, then you can figure out the height using similar kind of stuff with trigonometry. So it's a very practical way to take to figure out the lengths or angles that are not easy to directly measure. And it's all based on the relationships like sine, cosine, and tangent, and the ratios between these sides. So that's a good example. There's certain exact values that we know about these things, and I kind of want to go through that chart and make some observations to it, because there's values like tangent of 10 where we're just going to go with calculator answer, and that's fine. But there's certain exact values that come out nice that we'd really like to know because they show up a bunch. And the examples that we're going to do, and we'd like to be able to know the exact values of some things. So as I go through the angles up to 90, I'm going to go from between 0 and 90 degrees for now. 45 degrees is, of course, halfway in between there. So somewhere in here would be 45 degrees. Pretty nice angle to ask about some stuff there. And we're also going to think about what happens at 30 degrees and at 60 degrees, because those are both values that come out fairly nice. So my picture is not perfect, I'm sure, but somewhere in there would be 30, 45, and 60. Those all have pretty nice values of these trig functions. Work it out. Yeah, I'm going to look at the sine function first. Sine theta is y over r. So if I start with a point down here, the y is going to be equal to 0. And I'm going to work my way up through this quadrant. When I get all the way up to here, the y and the distance from the origin would be exactly the same because it's now moving horizontally. So the y value would be the same as the r, and sine theta would be equal to 1. So down here, sine theta is equal to 0. And at the top up here, sine of theta is equal to 1 at 90 degrees. And it's working its way up from 0 to 1 as we go through this. But the pattern with which it works its way from 0 to 1 is kind of easy to remember once you see the pattern here. So I'm going to look at the values of sine of theta as we go through that first quadrant. So as theta is going from 0 degrees to 90 degrees, we're working our way up from 0 to 1. But something clever that happens here that's worth seeing. Here's a funny way to write 0 and 1. And that is the pattern that we're going to follow for the rest of these through here. So Here's what ends up happening right here. 0 is the same thing as the square root of 0 over 2. That's a funny way to write it. 1 is the same thing as the square root of 4 over 2. And in between there, we actually fit, I'm sorry, over 2 is what I said. Square root of 4 over 2 is 1, right? So let me fix that. We're actually following that nice little counting pattern as we go in our sort of counting, right? This is the square root of 1 over 2, the square root of 2 over 2, and the square root of 3 over 2. So if you write your 0 and 1 in this funny way, then we do have this nice little sequence going on. It happens to fit nicely with these perfect values up here. That's why these are nice exact values to keep track of. Now the square root of 1 is just 1, so this is 1/2. These square roots don't come out so nice, but that's a fairly nice number to work with. Square root of 2 over 2 and square root of 3 over 2 are in there. So that's the pattern that sine follows as it goes up through that first quadrant. And I'm just trying to quickly give a lot of the basics right here. So if you can remember those values, then you have a ton of information. Let me build off from that. Cosine of theta is kind of doing the opposite direction here in the sense that cosine is x over r. So down here, x and r are the same. So your cosine is starting at 1. And you're going through that first quadrant to points up here where x is equal to 0. So that's going from 1 down to 0. And it's going through this same counting sequence in the other direction. So it works its way down from square root of 4 over 2 to square root of 3 over 2 to square root of 2 over 2 to 1 over 2 to 0. It just works its way down using that same pattern. So sine and cosine are pretty easy to keep track of with that pattern. And since tangent of theta is y over x, or opposite over adjacent, it's also the same thing as sine divided by cosine. So quickly moving through this, I know, but if I know what sine and cosine are doing, I can just divide them to get what tangent is. So 0 divided by 1 is 0. 1/2 divided by square root of 3 over 2 simplifies. It's 1 over square root of 3, or if you write it, rationalize the denominator, you get that. Sine divided by cosine, when they're the same, dividing them gives you 1. This divided by that is this regular square root of 3. And 1 divided by 0 is undefined. So up here, tangent is undefined because it's a division by 0. Tangent's y over x. And at 90 degrees, x is 0. So those are the nice values of tangent at those points. So we have all of these little facts from that the tangent of 45 degrees is 1, and the tangent of 60 degrees is the square root of 3, and we can build all of those things up. Even these weird functions like cosecant theta, if you just remember what it is in terms of these other ones, it's the reciprocal of sine, and that's the way we want to think of it. Anytime you see a cosecant, you just want to think it's 1 over sine theta. It's the reciprocal of sine. So it's undefined right here because you can't do the reciprocal of 0. And these other reciprocals are easy to do. That's 2. This over that, 2 over square root of 2 simplifies. This over that, 2 over square root of 3 should be written using rationalizing the denominator, I guess. So that gets a little worse. And 1 over 1 is still 1. So those are, you can generate the values of the other things if you know what happens with sine and cosine. And sine and cosine just come from those nice count sort of counting pattern with the square roots. And so those would be good ones to remember. We're going to use those a lot in the exercises and get comfortable with those values and be able to use them as you go. So that's what's happening in, for instance, exercise number 63. We got to get used to some of the language, some of the terminology that shows up in here. Let me explain what's happening on this. Number 63 in this section says to find the measure of the acute angle theta whose sine or cosine is given, and for this I have sine of theta equals square root of 2 over 2. So we're trying to find the actual value of theta on this one. That's what they're asking for. What is the angle for this? Now, acute angle, if you remember your geometry terms, acute just means it's less than 90 degrees. So that's somewhere between 0 and 90 degrees. Then this is the first quadrant. Acute angles are just first quadrant ones. And that's what we just had written down. Nothing's negative in the first quadrant. You're working through these values that we just had written down. So where sine of theta is equal to square root of 2 over 2 is right there on my chart. I'm just going to work with that. Sine theta is equal to square root of 2 over 2 right there. That's where it hits it, is at 45 degrees. So that's the acute angle theta where that's true. We're just using the chart backwards. Now, if I didn't have one of those nice numbers, I wouldn't be able to do anything like that. We should also think about how this would happen in the calculator. What if I want to know theta, and this isn't one of my nice magic numbers that happens to be written there? I should still be able to figure out theta from that, and undoing this function is what I'm trying to do. I have a little equation, and I want to get rid of this function. It's another inverse function situation where I want to know the input, and I've got the output of the function. So there's an inverse function for that. It's inverse sine, and that's in the calculator also. So we want to know how to use that. If you haven't messed with those yet, we want to find in your calculator. It's usually right there with the sine button. Right up above the sine button is this. I can't hardly read it on here. Says inverse sine, and it's written in yellow here because I have to use this shift button to get to it. So there's usually a modifier thing to get that inverse sine to happen. I'm going to hit shift sine, or it's on a TI calculator, it's second sine. That's the modifier button that does it. And I'm going to put container in there because this is a function of. And then I can put in the output and get theta out of it. Square root of 2 over 2 should come out nice. So I'm going to put square root of 2. Divided by 2. You know what, I need some containers there to make sure I'm only taking the square root of 2 right there. So square root of 2 divided by 2, inverse sine is 45 degrees. That's the value. And I could use that to find the angle of other stuff, even if I didn't have nice values like the ones that I drew on here. I'm sure we're going to get to that. We want to be able to work with other angles also, and that's coming up. So I'm going to think about it while we're on this kind of problem. So I'm going to think of some weird number like this, how to find theta. I'm just going to do the inverse sine of it. Is how I'm going to calculate that. But on the picture, this is what's happening. My angles from 0 to 90 are the first quadrant, and sine theta equals 0.972. That means y is 0.972. So this goes up as far as 1, the y value, if I'm talking about points where r equals 1 on this unit circle here. The y value works its way up from 0 to 1, and 0.972 would be almost there. So 0.972 is just slightly under that. I'm going to get some angle just a little bit less than 90 if I work through that. So I'm trying to find theta. I have to undo the sine. That's the inverse sine function of 0.972. Another decimal point there. 0.972. Inverse sine of that is 76.4 degrees. So that would be approximately 76.4. I don't get an exact value for that. I get an approximation that theta is about 76.4. That's what you get from the calculator. So that's a useful thing to be able to get the calculator to do also. What else was on the homework here that we might run into? I want to get into the third section, I guess, a little bit. I have on this week's homework some of this thing from T3, so like 40 and 45. I want to make sure we've talked about some of the stuff from there. So we go up to that section. Some of the exercises from here. They're on these exact values. Okay. Here's number 40. This is actually in the homework right here, but we're going on to section 3T3, number 40. And there is some stuff to introduce in here. It says find the exact value of the given trigonometric function. So this is one of the ones we know exact values from, but it's moving out into some other quadrant. Now 7 pi over 6 is not a degree measure here. This is in radian measure. So instead of dealing with those degrees I was talking about, we have to think about what that means in radians. And let me introduce that on the picture, and we'll look at how to convert back and forth between these things a little bit. But I want to think about where that is on this picture. The radian idea makes some sense up here. For degrees, for some reason, it was decided that one complete revolution would be 360 degrees. That was the thought process. 360 is divisible by a bunch of stuff, so it was a nice number to use. Very convenient, and people are comfortable with it. Radians is actually a more geometric idea that if you look at the actual distance around that circle, circumference formula says if the radius is 1, then the diameter is 2, and the circumference is going to be 2 times pi then. So all the way around that circle would be 2 pi, the distance around it, and that's what we use for radians. We're going to say one complete revolution is 2 pi radians. So 180 degrees would be halfway around, that would be at pi radians. And half of that would be 90 degrees, would be the same as pi over 2 radians. That's a sensible system to use also. That's the radian stuff. And these multiples of pi that we're looking at in this problem are probably, that's a radian measure. So if I think in terms of pi over 6, if I divided this in 6 pieces, that's 1, 2, 3, 4, 5, 6 is 6 pi over 6 would be pi. So another sixth of that would be down here somewhere. Another 1/6, that's 7 pi over 6. Pi over 6 is the same as 30 degrees. We got 1, 2, 3, 4, 5, 6, 7 of those. Gets you over here. It's the same as 210 degrees. If you want to do the conversion, we're using the fact that pi radians is the same as 180 degrees. So 180 degrees is the same as pi radians. That's the conversion then between these two things. Radian measure times 180 over pi would turn it into degree measure. The pi's cancel. 6 goes into 180 30 times, so this is the same as 210 degrees. But once you get used to the picture, you don't need to convert it to know where it is. You can see this is a little more than pi. You can see it's going to extend down into that third quadrant a little bit. It's negative x and negative y down here. So the cosine is actually going to come out negative. Cosine is x over r. It's the x value over here, which is going to be negative. And we could get the calculator to do this, but we don't really need that because our nice exact values were here. This picture over here, that's obviously a negative x value, but it's the same point that I would have been up here when I was at pi over 6. This is the mirror image of that. So the cosine of pi over 6 was this x value. square root of 3 over 2. So for over here, it's just going to be the negative of that. It's going to work its way down. That's the kind of stuff we can get used to thinking through on this picture. So that once we know these nice values in the first quadrant that I had on the chart there, it's just going back through the same stuff, maybe with opposite signs. So cosine starts at 1, square root of 3 over 2, square root of 2 over 2, 1 over 2, down to 0. And then it starts to go negative, negative 1/2, negative square root of 2 over 2, negative square root of 3 over 2, negative 1. And this is still back to negative square root of 3 over 2 in this third quadrant. Same values, just positives and negatives. And so that unit circle picture helps us keep track of the different signs on things. We can confirm that calculation-wise. We can go back over here and say, now I'm using radians. I got to change that mode again. So in my angles here, I got to change that over to radians. And I'm going to do cosine of 7 times pi over 6. And that comes out negative. And here's a great big decimal right there, but I believe that's the same as this value. I can confirm it this way. If I do negative square root of 3 divided by 2, that's the same value right there. So let's check that this works out. That looks good in the calculator. We got negative square root of 3 over 2. And so when you know some stuff about those exact values in the first quadrant, you can extend that out and kind of wrap it around to values in the other quadrants. And everything works using the same values. You just got to keep track of what's positive and negative. In the picture, you're used to where x is negative and where y is negative. You're used to those things on the picture. So there's a lot we can do with that picture once we get used to it to kind of save us a lot of work and know some exact values about a bunch of other locations on it. So there's some nice images out there. There's some nice charts that show all of these values from 0 around to 360. They would also show these things in radian measure, which is these fractions of pi. And you could find your sine and cosine on there from the XY coordinates of these things. There's some nice charts that have all those values on them. We want to get used to that as we have a bunch of questions that are going to ask about those exact values of things. You'll see that. Quadrantal angles. I don't know if they have a nice summary in this, but I was just looking for a nice summary. They might have one at the end of the book, but not really in here. Okay. So we did number 40 there. Let me look at 45 also while I'm on the topic. We'll get to some of these. So 45 is asking for the secant of 150. Don't have a secant button on the calculator. I don't know secant values right off the bat, but I know it's the reciprocal of cosine. That's how I'm going to think about that. Anytime I see a secant, I'm going to think this is the reciprocal of cosine. So I'm just going to do 1 over. Well, I have to think about what the cosine of 150 is. So 150 degrees is going to be in that second quadrant some. If I think about the picture now, I know stuff between 0 and 90 degrees. I'm back in degree thinking. But if you go past 90, this is 180. So 150 degrees would be straight across from what happens here at 30 degrees. Same kind of values, except x is negative over here, so cosine is going to be negative over here. So I can tell that's going to be negative, but numerically the x that's there is the same as the x that's here, just the negative of it. And this was, for cosine, this was working its way down. So square root of 3 over 2 is the cosine value right there. So I can fill that in. It's going to be negative. It's the reciprocal of square root of 3 over 2. And since that's a fraction, the reciprocal of it just flips that over. So that's 2 over square root of 3. Or if you're into, that's the right value, but if you're into writing it with rationalized denominators, we can do times square root of 3 over square root of 3. You can get that written using a nice denominator there. Kind of running through this stuff, kind of get basic introduction to a lot of the ideas that show up. That's the best I know how to handle this video introduction. You've got, of course, little videos tied to the problems in the book, but not having any questions to work with us. The best I can try to do is toss a bunch of the ideas out there so that this will be useful to you if you're watching this later on. As you're working through this homework, you can go through this and can it make some connections between these ideas, I hope. All this trigonometry stuff has nice pictures. And if you work through this stuff without looking at the pictures, it can seem like a great big mystery. But if you do your little sketches or look at the sketches that are done in the book already, see how this stuff works together geometrically. It's all describing shapes. There's pictures behind everything. So you want to work with the diagrams and pictures whenever possible. So I'll leave this video up. Hope it's helpful to some people as you're going along through this work. Let me know what you run into on that homework. If you have some that you get stuck on, there's a lot of ways to ask questions here. So it can be kind of hard to understand what they're doing, what they're asking for. But I like having those videos right next to those exercises as you go along. I think that's going to be a help to people. Lumen work where you can practice a bunch of this stuff, but let me know if you run into any of these that you don't know what they're asking for, you get stuck on that. Send me some questions. You got, I put up a correction because in my original announcement on Monday, I said that the homework was due Tuesday, April 10th, which doesn't go together. Friday is April 10th, and that's what I meant. These are due Friday. So I want to get these homeworks in this week, and then we'll do a little bit more trigonometry applications, and then we're back to algebra at the end of the semester. So a couple weeks to go on this stuff before the final exam. Hope things are moving along okay for you. Keep in touch. Let me know if you have any questions. I'll talk to you all soon.